Hi, this is Mr. Mack. This is a concept video on probability. Probability is a mathematical measure of how likely an event is to occur. Now, we need to start talking first about sample space. Now, sample space is a phrase that we use to describe or to talk about all the things, and I'm going to put things in quotes here, that could happen. For example, the sample space for flipping a coin would be, let's use set braces here, heads and tails. The sample space for flipping a coin twice would be heads, 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 tails, tails, heads, tails, tails. So notice when we're talking about a sample space, we're just talking about all the things that could happen in that particular situation. Now, a lot of times we'll talk about an event. An event is, actually mathematically, it's a subset of the sample space. For example, in this second example that I gave here, we could say, let's let A be the event heads, heads. So it's one of the elements in the sample space, so event A is heads, heads. Now, we're ready to define probability. Now, the probability of an event, and usually we'll do P of A, the probability that event A occurs is equal to the number of ways, or the number of elements in A divided by the number of elements in the sample space. In other words, in this case, the probability of event A would be 1 element in the sample space is heads, heads, over 4, because there are 4 elements in the sample space. So the probability that we will get, that event A will occur is 1/4. And this is pretty much all probability is. You count up the number of ways you could be successful and divide by the number of things that could happen. That gives you the probability. Now, since we are counting, it is kind of important for us to know something about counting. And so I'm going to include this here, although it's not in this section of the book. It actually must have occurred in some other section. One I think that we haven't covered, because I don't recall covering counting this year. And if we have, that's probably because I'm getting old and I just don't remember doing it before. But I really suspect that we haven't covered this. So first of all, in counting, there is a fundamental counting principle. And this is very, very important for you to know. You probably know this already, but still, let's make sure we state it formally. If you want to count the number of ways something can happen, you can split the something into discrete sub-events, in parentheses, all of which must happen, then the number of ways the event can happen is equal to the product of the number of ways each sub-event can happen. Now, I know that took a while and it may not make a whole lot of sense yet. So let's take a look at an example that'll help you with the fundamental counting principle. Imagine that you want to get dressed. Okay, so the event is get dressed. Now, further, let's imagine that you have 2 pairs of slacks, 3 shirts, and 2 pairs of shoes, all of which will go together. The question is, how many ways can you get dressed? Well, now, what we're going to do is we're going to use the fundamental counting principle. We're going to split the event, get dressed, up into put on slacks, put on shirt, put on shoes. Now, we go to the first event, put on slacks. Put on slacks. How many ways can we put on slacks? Well, since we have 2 pairs of slacks, there's 2 ways we could do that. I know, I guess we could put left foot in first and then right foot, but we're basically talking about how many different pairs of slacks could you be wearing? 2 pairs. Okay, then the second event is going to be put on shirt. Okay, now how many ways can you put on a shirt? Well, since you have 3 shirts, there's 3 ways to put on a shirt. You choose a shirt, put it on. There's 3 different choices. And then the third event will be put on shoes. I'm running out of S-H-O, put on shoes. Put on shoes. How many ways can you put on your shoes? Well, there's 2 pairs of shoes. And assuming you're not going to put one from one pair and another from the other pair on, there's 2 ways you could do that. Now, how many ways can you then get dressed? Well, the fundamental counting principle says it's the product of these things, so it's 2 times 3 times 2, or 12. Now, there's a number of different ways this could be asked. Also, we could say you have 2 slacks, 3 shirts, 2 pairs of shoes. How many different outfits can you wear? And it sounds a little different, but it's exactly the same question. So when you're trying to count something that is kind of a complex process, if you can split it up into discrete parts, all of which have to happen so that the big event happens, and then you can count the discrete parts, the number of ways for the big event to happen is the product of the ways for each of the little events to happen. That's the fundamental counting principle. All right, now, the next thing about counting that we need to talk about is sometimes we question how many different ways can we select something out of a group. So let's imagine we have 5 cards, a 1, a 2, a 3, a 4, and a 5. And we're going to choose 2 of those cards. And the question is, how many different groups of 2 of those cards can we choose? Well, first of all, let's just go ahead this time and list them. We could have 1 and 2. We could have 1 and 3. We could have 1 and 4. We could have 1 and 5. Now, we're not going to mark 2 and 1 because we just said how many different groups of 2 cards. And 2 and 1 is, if we don't care which one we got first, is the same thing as 1 and 2. So, but we do have 2 and 3, that's different. 2 and 4, 2 and 5, those haven't been listed yet. And then we're not going to do 3 and 1 and 3 and 2 because we already have those if we don't care about the order. But 3 and 4, and then 3 and 5, and then finally 4 and 5. Now that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different groups of 2 cards that you can take from this deck of 5 cards. Now, there is another way to count this. It turns out when you're selecting objects out of a larger group of objects, the number of ways it can be done is always one of the binomial coefficients. And so, for example, in this case, we have 5 cards. We're selecting 2 cards. The number of ways it can be done is 5C2. Now, that would be 5 factorial over 2 factorial, 3 factorial, which is 5 times 4 times 3 times 2 times 1 over 2 times 1 times 3 times 2 times 1. Now notice the 3 times 2 times 1s cancel out, and the 2 will cancel with a factor of 2 and the 4, leaving 10. And look what we've got. So when you want to find how many ways you can take a subgroup out of a larger group, if you don't care how they're arranged after you take them out, you use the binomial coefficients, NCR. Now, sometimes when you're taking these things out, the way they're arranged is important. Let's imagine we have a club. And in the club, there's Al, Betty, Charlie, David, and Eugene. Okay, now we're going to say how many different ways can the club elect a president and a vice president from these 5 individuals. Okay, now if we were to list these, we would have to realize that the president and the vice president, if they were the same people, it would actually be different. So if Al was the president and Betty the vice president, that would be different from Betty being the president and Al being the vice president. So let's go ahead and list all of these. This list may be a little bit more extensive. We could have Al and Betty, Al and Charlie, Al and David, Al and Eugene. We could have Betty and Al. We could have Betty and Charlie. We could have Betty and Dave. We could have Betty and Eugene. Okay, what happened here? I'm going to do another thing here, president, vice president. We could have Charlie and Al, Charlie and Betty, Charlie and David, Charlie and Eugene. We could have David and Al, David and Betty, David and Charlie, David and Eugene. I need some more room here. Let's move this all over here. And the third one, we could have president again and vice president. Vice president, we could have, well, we got through with David, so we could have Eugene and Al, Eugene and Betty, Eugene and Charlie, Eugene and David, and Al, Betty, Charlie, David. We don't have Eugene and Eugene. So now, what have we got? We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So there's 20 ways that we could select 2 out of a group of 5 people if the order that they're selected is also important. Now, one of the things about mathematics is a lot of times there's more than one way to, if you will, skin a cat. So let's just take a look at at another thing here. We'll use the fundamental counting principle, and we're going to use a tree diagram. So now let's start out. We're here at this point, and we're going to say we're going to elect a president. Now, how many ways can we elect a president? Well, 1, 2, 3, 4, 5, right? So this would be Al, Betty, Charlie, David, and Eugene. Okay, now, let me just do something a little strange here. Okay, maybe that's a little bit too small. There we go. Now, oops, that's not what I want to do. Just delete that. Okay, let's pull one of these out. And I'm going to erase these letters. No, let's just do this. Okay. Yeah, there we go. Okay, now, if Al is elected president, then we have 4 different people that could be elected vice president. Betty, Charlie, David, Eugene. If Betty is elected president, then we have 4 people that could be elected vice president. Al, Charlie, David, Eugene. If Charlie is elected president, then we have 4 people that could be elected vice president. Al, Betty, David, Eugene. If David is elected president, then we would have Al, Betty, Charlie, Eugene that could be elected vice president. And if Eugene was elected president, then Al, Betty, David, Charlie could be elected vice president. Now, actually, notice we've got 5 branches here, and then for each of the 5 branches we have 4. So the number of different things we have here is 5 times 4, or 20. So again, we get 20 from this in this particular way. Now, it turns out that if you want to find out how many things can be done where the order counts, in other words, if the same people or same things chosen in a different order is considered different, then we would use this method of counting. In other words, how many choices for the first one, and then after that, how many choices for the next one, and so on like that. And there is a way of doing this. In other words, NPR will actually compute this for you if it gets large. And that's in your calculator. It's like the 4th. You remember NCR was the 3rd one down into the probability under the math menu, and NPR is the 4th one down in the menu, in the probability menu in the math menu. So you can use NPR. It works just like NCR. But now that will allow you to count things, whether they're in order or if they're not in order. Now the next thing that we want to talk about is probability distributions. Now, statisticians talk about a random variable. Now, remember, a variable is an unknown, something you don't know, so you use a variable in place of it. Now, a random variable means that you've got something that's going to happen, something will happen, and you don't know what it is. Okay, for example, if we're going to roll a die, die is the singular of the plural dice. And remember, die is a cube, and on the 6 faces of the cubes we have dots 1, 2, 3, 4, 5, and 6. So if we roll a die, we say that the number selected is the one that's face up. And so when we roll a die, the random variable, and we'll use X for the random variable, could be 1, 2, 3, 4, 5, or 6. So those are the different outcomes. Now, the probability of those outcomes is theoretically 1 out of 6 for 1, 1 out of 6 for 2, 1 out of 6 for 3, 1 out of 6 for 4, 1 out of 6 for 5, and 1 out of 6 for 6. Now, this would be a probability distribution. In other words, we list all the things that could happen, and we list all of the probabilities. So when they ask for a probability distribution, you put down the different things that could happen in one column, and then you put the probabilities of each of those things in another column. Now, they're not always going to be the same probabilities for each event, but in this particular case, it is. Now, the next thing that comes along is the concept of expected value. Now, expected value is if we roll a lot of times, you know, if we took a die and we rolled it a lot of times, what would be our average? What would be the average of the numbers that come up? Now, the expected value can be computed by the sum of each random variable times its probability. Okay, and so that's this. Now, in this particular case, the expected value would be 1 times 1/6 plus 2 times 1/6 plus 3 times 1/6, that's times there, plus 4 times 1/6 plus 5 times 1/6 plus 6 times 1/6. And so you take each random variable or each event that could happen and multiply it by its probability and add them together, and you get the expected value. And so that's okay. Now, that concludes the concepts that they wanted to talk about in this particular section. Okay, now some of the problems seem to be fairly complicated, so give those a try, and then after I've taken a look at the journals, I will post the videos on how to do those problems later. So we're done.